welcome to my talk. I'll start with some introduction about myself. My name is Noman Abbas, and I'm the engineering manager on the observability team at Pintrace. My team, we're responsible for building monitoring and observability tools like our metric system, alerting, Logsearch, distributed tracing. And before Pinterest, so I've been at Pinterest for 3 years now, and before Pinterest, I've worked at companies like Netflix and Microsoft. All right, so what's Pinterest? So Pinterest is a web and mobile app. If you have not used it before, it's an app to discover ideas, search for different things, search for your hobbies or those kind of things. Our mission is to help people discover and do what they love. And we're a pretty big company now. We have 300 million monthly active users. They have saved 200 billion pins on our app, and we have 2,000 employees. So we're a decent-sized company. We're growing pretty fast, and we were facing all the challenges that companies, when they are at this stage, they face. So here's the agenda for the talk. We'll start with why observability. What are the challenges that we are trying to solve by different observability tools, and how it can help us with those challenges. Next area would be observability tools. These are I'll cover some of the tools that we have at Pinterest that we use in our day-to-day operations. Third section would be around the evolution of these tools. We have been working, basically adding a lot of features to these tools. I'll cover some of the example cases for the work that we have done. And then the last section would be lessons learned. We'll quickly go over some of the key things that we learned over time. All right, so why observability? Similar to most of the modern software services, Pinterest is built on a microservice architecture. In this architecture, how it works is there are hundreds of services that work together to serve a single user request. So at high level, this is how it looks like. We have a client, or we have lots of clients. They send the request to CDN. From CDN, the request goes to some API service, front-end API service. From there, there's usually a big fan out to back-end services. And then there are lots of services in the back-end. They work together and deliver user requests. So this architecture provides us with lots of benefits, like you can have a smaller code base, you can have faster deployments, your teams are decoupled, those kind of things. But while we have these benefits, there are some challenges of this kind of architecture as well. Here is the service dependency graph for Pinterest software stack. So on the left side, you can see we have clients. They're going through CDN, then API service, and then there's a big fan out. And we literally have hundreds of services in the back end. Some of these services are not even on this graph because we built this using our distributed tracing system, and it doesn't cover all the services. But you can see how complex the system can get. And in an environment like this, basic things like how a request is being served or how the system is working can be challenging. Just understanding this can be challenging. And then if there is some incident going on, there's some problem with one of these services or number of these services, it's really hard to pinpoint what's the source of that problem, finding the root cause of that problem. And third thing is, we want to move fast. We want to deploy new versions of software. So whenever you deploy something, make a change, there could be unexpected outcomes or side effects from that change. So in a complex system like this, how do you make sure that you can deploy, make updates at a fast iteration? So for these kind of challenges, we have observability tools. They can help us for some of these challenges. Let's look at the change cycle. So again, like I said, most of the companies, including Pinterest, we want to move fast. We want to add new features. We want to try new things. And for moving fast, this is how, for making any change, this is how the change cycle looks like. In this change cycle, we're focusing more on observability. So it's basically focused around the observability part of the change cycle. So on the top, we have the state where we want to make a change. This includes a lot of things, like when you're designing a code, designing your software, writing code, writing test, all those things. So again, in one stage, I've captured all those things. So a lot of work goes in making a change. Once you are confident about your software or your change, you deploy it. Once it's deployed, you want to know how good or bad that change is doing. You want to measure a few things. So you expected certain behavioral change in the system after deploying that change. You want to verify that. So that's where the monitoring tool comes in. You can use it to measure different things. You can use it to add alerts on top of your services to make sure if anything is breaking, you can get alerted. So yeah, once monitoring system finds some issue with your change, it can throw you an alert, or you can look at some dashboard and see, hey, something is wrong. Then comes the next phase, where you want to find the root cause of that change. And that is the debugging phase, where now you know there is something wrong in your system. You want some tools to find out what's wrong and what's the root cause of that problem. You use observability tools, find the root cause, and then make another change or revert your earlier change, and then go back to the change state. So this cycle keeps on going as we move forward and we add new features, new changes to our system. And as a company, the goal is that this cycle should move fast. You should be able to make these changes really fast. And you should be able to make these changes with confidence. You shouldn't hope that things will work once you deploy your change. So that's where the monitoring and observability tools come in. They should be able to provide you that confidence, that reliability, that I'm going to make a change, and then I should be able to see how that change is doing in the system. All right, so next section is observability tools. We have three main tools. The first one is Statsboard. It's our metrics tool, so it's used for all the operational metrics. It's built on top of OpenTSDB, and we have a web UI and an alert service that's built in-house. This screenshot is from the web UI. Our users use this tool to build dashboards for their services, so they can build dashboards. They use it to look at different metrics from their service. They also use this tool to add alerts for their services. It's very common to use it for debugging and performance tuning. So if they have any latency metrics or those kind of things, they can use this tool for performance tuning. This is one of the main tools that people use for debugging and for other monitoring use cases. We have around 2,000 dashboards defined in this tool, and we have 16,000 alerts running every few seconds. So yeah, its scale is big, and like I said, it's one of our main tools. We put in a lot of resources and energy on maintaining and scaling this tool. Next one is Logsearch. It's used for basically sending debug logs to a central place and then a web UI where you can search for those logs. We use ELK stack for this, and we use AWS hosted ELK, so that's really helpful. Most use cases for this tool are basically root cause analysis, so logs usually have more context in them. You can look at a lot more details in the logs that are lost in metrics. So that's one of the use cases where people use this tool. The second use case is alerting. So we have integrated this tool with our metrics tool, Statsboard, the one that I showed earlier. And basically, you can add alerts on top of your logs. So for example, you can add an alert on number of exceptions or new exceptions or those kind of things. Third tool is Pintrace. It's our distributed tracing system. It's built on top of Open Tracing APIs and Zipkin. We use Zipkin UI to look at the traces. The screenshot is from one of the trace. This tool is mostly used by our performance team. This is the only tool that gives you that end-to-end latency breakdown. So it gives you the full view of how a request is served by your system, how much time is spent on each service, how much time is spent on network, those kind of things. So yeah, this is very, very useful for performance tuning and those kind of things. Second thing is root cause analysis. Again, since it gives you a full view, it helps you in finding the root cause for different problems, and I'll show an example where this is super helpful. So, evolution. Before we go into the evolution of our tools, let's first look at the observability needs. So, let's see that what's the needs hierarchy for different observability tools. The first need is reliability. So any tool will not be useful if it's not reliable. By reliability, what I mean is that the tool should be available. So let's say there's an incident going on, and you go to your metric system or your Logsearch, and if the tool is not available, that's bad. So the tool has to be super available all the time, because without that tool, you're flying blind. You don't have any information of how good or bad the things are doing. Similarly, another area of reliability is trustworthiness. So you should be able to trust your tool. If it's giving you a value for a metric, you should be able to trust it. If the tool can give you random information, then again, the tool is not very helpful. Similarly, if you're getting alerted from the tool, you should be confident, you should have this confidence in the tool that those alerts are not false positives or false negatives. If the tool is just sending you alert storms without any reason, then again, it can be very stressful. And then again, it can add a lot of noise to the system. So once we make our tools reliable, second thing is to make them user-friendly, easy to use. What this means is that shouldn't be a challenge to use the tool. You shouldn't be fighting with the tool. Things should be discoverable. I've seen cases where some of our users, they find a feature that's hidden somewhere in the tool, and they're super excited. Hey, this is awesome feature. Why didn't I know about this sooner? So again, if that's the case, then your tool was really good. It had all those features, but they were not user-friendly. They were not discoverable. So yeah, this also helps a lot in improving the engineer productivity. So you want to make sure that the engineers, they are not wasting time on the tool. They are they're doing more productive work than just spending time on using the tool or understanding the tool or configuring the tool. And the last one is automation. So, I mean, we want to automate things. We want to take human out of the picture, because humans can be slow. They can make mistakes. It's hard to scale them. They're expensive, all those things. So automation can also really help us with having a good observability and help us move fast. So we'll start with looking at tools reliability. Again, we've been doing a lot of work around tools reliability, but I'm going to focus on some of the key examples. So the biggest challenge that we have for tools reliability is our growth. We're growing really fast. We're growing at a super linear speed. Right now, our metric system is processing, it's almost hitting 1 billion metrics per minute. So that's a lot. And again, you can see the growth graph. So in the last 3 years, we have grown almost 10x. In the last 1 year, we have grown 4x. So your tools need to handle this kind of growth. If they can, then their availability can go down. So how do we make sure that our tools are available? We keep evolving their architecture. So for example, for our metric storage, we started with Graphite. This was, I think, 5-6 years ago. But after some time, the system was unable to handle our scale, so we moved to OpenTSDB. That worked fine for some time, but then we started hitting its limit as well. So what we did was we started sharding our OpenTSDB clusters. And right now we have almost, I would say, 10 clusters, and each cluster has some replicas as well, so that if one cluster goes down, we can read from the replica. So it's a lot of work in managing those clusters to make sure they're all they are all available and serving traffic. And for last almost a year and a half, we've moved to an internal tool. We called it Goku. It's an in-memory time series storage system. It's built on top of Facebook's Gorilla algorithm that gives you really good compression for time series. And with that kind of compression, you can store your data for last 24 hours in memory. So that has been working out really well for us. For most of the users, they're more interested in last 24 hours. So most of our requests go there, and it's super fast because it's in memory. And it really helped us scale our system to the next level. Next is metrics processing. So again, our scale is pretty big, and we have to do a lot of processing on top of our metrics as well. This includes things like roll-ups, pre-aggregation, processing, even logs, those kind of things. So we started off with Storm. Then once we hit its limit, we moved to Spark streaming. That also worked pretty well in the start, but over time we realized that it can be a little bit unstable and it doesn't give you full control. Then we moved to an in-house tool. We call it JobStream. It's built on top of Spark. It's similar to Spark streaming, but it gives us more control from where we want to read and write data. And it really helped us in doing backfills and replays and those kind of things. So yeah, we've been evolving our tools architecture to handle the growth of our system or our users. Another way to handle growth is to kind of compress or reduce the amount of data that you're generating. So basically, it's reducing the cardinality of your data. For example, in this case, what we do is we do metrics aggregation by service. So for example, let's say you have a service that runs on 2 hosts. So each host is generating its own metric. And usually what we do is we add a host tag with those metrics. And each of these metric is a unique time series in the data store. And if you have a service that's running on hundreds to thousands of hosts, that's adding a lot of cardinality to that metric. So what we do is we have a Spark job that aggregates these metrics into a single metric for that service. So in certain use cases, you don't want to look at metric per host. Even the metric at the service level is good enough for you. So this is giving us really good savings. In certain cases, we're able to reduce the data volume by 99%. And it's good for basically reducing the cost on the storage side and on the user side as well. When they are trying to read these metrics, they're super fast because you have to pull less amount of data to look at these metrics. And the last thing we do to reduce our data is chargeback. So the idea here is you incentivize your users to generate less data. So if everything is free, if everything is unlimited, everyone will keep adding more and more metrics. That's how you get that kind of exponential growth. What this tool does is it gives you a good breakdown of how different services are consuming the resources of your metrics pipeline. And we have a similar tool for our log system as well. And in this graph, you can see that one of the service, the one in red color, it was consuming around 40% of our metrics pipeline resources. So that's a lot. So we worked with that service. We shared all the details. We helped them reduce the cardinality of some of their metrics. And after that change, the usage went down. So yeah, that's another way of reducing the problem size so that you can continue serving your users. All right, next section is tools usability. So again, we continue improving our tools to make them more user-friendly, easy to use, faster to use. One example here is TScript. So this TScript stands for a scripting language for time series. Usually when you want to look at a metric, you don't want to look at raw metric. You want to perform some operations on top of it. For example, you want to maybe divide some series with some other series or add series, do a time shift, calculate success rate, those kind of things. So before TScript, we had some functions that you can apply on top of your metric, and then you can nest those functions inside each other. But with TScript, it looks a lot more like any programming language, where you can assign variables to metrics, and then you can apply functions on top of that, and it's almost like you're writing code. So here in this example, what we're trying to do is we're trying to compute the percentage difference, week over week percentage difference on a metric. On the left side, that's how we used to do earlier. On the right side, you can see how simple it is. Basically, in 2-3 lines of code, you can do this. So this scripting language is super powerful. Our users, they have really liked this thing, and it has really opened a lot more opportunities for them to manipulate data and apply different functions on top of it to get a better understanding of their things. Next one is integrated alerts. So before this feature, how alerts worked were we had 2 separate configurations. One for our dashboards, where you can go and configure your dashboards, define them through YAML config. And the other configuration was a completely separate configuration for your alerts, where you define alerts. What would happen is, over time, both of them, they would go out of sync. So let's say you get paged at late night, you open a dashboard, and it's completely different than, you have no clue why that alert got triggered. You have no context of why you got paged. With this thing, since the alerts are defined within the dashboard and they're part of the graph that contains the metrics that were used for that alert, you can quickly see that what metric or what change triggered that alert. And then we also have change feed, basically integrated with our dashboard, so you can quickly see that, okay, this deployment caused change in this metric value, and that's why I got alerted. So this also is really helpful in basically for SREs or in general for on-calls to see what's going on in their system. Next one is Quick Dash. So the idea here is a web UI to build dashboards quickly. Before this, we had a YAML configuration to create dashboards where you would define sections and metrics and those kind of things. With this, you can do everything on the web. So you can just drag and drop graphs on it. You can move them around, resize them, and then you can just click the Save button, and you have a dashboard. And if you want to edit it, you can go back and edit it very quickly. One big use case for this dashboard is users who are not developers. So before this, you had to commit your change in a repo. And again, if you're not a developer, then it's a big barrier for you to basically use this tool. With this, basically anybody can create a dashboard. And the last one is RunDash. So again, the idea here is similar to integrated alerts. Before this, or even now, a lot of people don't use it. It's not that widely used right now. But the thing is that usually you have a separate kind of a wiki page kind of thing for your runbooks, where you keep all the details on how to run your service, and a different tool for your metrics dashboard. With this, we have combine them together in a single tool where you can show and hide the runbook. And with this, they again stay in sync. And whenever you see that, hey, this runbook is out of date, you can quickly go and update that so that they never go out of sync. and you have a single pane to go to whenever there's an incident. You just go to one single page, and you have all the information that you need in that one page. OK, tools automation. So here's a quote from Google SRE book. Roughly 70% of the outages are due to changes in a live system. So like I showed you the change cycle again, we have to make changes. We cannot not make changes, but they can be very dangerous. And in a lot of cases, they are the root cause of outages or incidents. And this percentage is very true for Pinterest as well. So the first automation that we are working on is automated Canary analysis. So we have seen a lot of cases where we deployed something to a Canary, and that code had a bug in it, and we still deployed it to production, and then it caused an incident or an outage. And later on, when we went back and looked at the metrics were there, but nobody looked at those metrics. In this case, the idea is to automate this whole thing. So the way it works is we deploy the new version, the Canary version, to a small set of hosts, and then we deploy the production version in another small set of hosts, which is the baseline. And both of these clusters, actually all three of them, production, baseline, and Canary, they all get production traffic. Then you look at the metrics that are getting emitted from baseline and Canary, you compare them, and you see how good or bad Canary is doing versus prod. And the automation here is that there could be a tool that can do it for you, where you don't have to do the comparison. The tool does it for you, and it gives you a thumbs up or a thumbs down based on how good or bad that service is doing. If it's really bad, you can configure your deploy pipeline to roll back or take some action. So for our deployment pipeline, we're moving towards Spinnaker. And with Spinnaker, there's another tool that's called Kayanta. It's built by Netflix, and it's an open source tool. So we're using that for our automated Canary analysis. This is a screenshot from that tool that kind of shows you what metrics were added to that tool, and again, which of the metrics were passing and which of them were failing. Next area is automated root cause analysis. So we have seen earlier that, again, in a big complex environment, it's really hard to pinpoint the root cause for a problem. For example, in this case, let's say there was some issue with service C, and that caused problems for service B and service A, and then your API was also seeing some kind of errors. It can be really challenging to find the root cause in an environment like this. If there's a major failure on service C, then you might be able to catch it sooner, because if everything is breaking, you should have some kind of alerts around that. But if it's a minor failure, there is a small subset of requests are failing, or there's a latency increase for a small set of requests, then it can be really challenging to pinpoint that small failure. So for this, distributed tracing can be really helpful. For example, here is a trace for a request that was failing at the API level. And we can see the breakdown of how that request was served by the backend services. And each row that has red dot in it means that there was an error in that service. By looking at this kind of view, I think it's pretty easy to see what the root cause of that failure was. In this case, it was the data service that failed, and then the services that were calling the service also started failing because their underlying service was failing. So imagine if we can build a tool that can do this job automatically for us, so you don't have to basically look at traces, but the tool does it for you. One problem with distributed tracing is that one trace can be an outlier. So it's really hard to look at multiple traces, so you need some kind of tool that can give you that aggregated view for your traces. So what we have built at Pinterest is a tool. We call it Trace Analyzer. And the goal of this tool is to do the root cause analysis for latency regressions. The problem that we were trying to solve was that, for example, you see latency increase in week-over-week values or month-over-month values. So over time, slowly latency is going up, and after some time, you see, let's say, 5% increase. Now, since that increase is not coming from a single change, it's really hard to find what backend service out of those hundreds of services is contributing towards that latency increase. So what this tool does is you give it a time range. You say, hey, compare 1 week ago or 1 month ago with today, and it will pick some traces from 1 month ago, do some analysis on them, some traces from today, do some analysis on them, and then it's going to compare the results. So these graphs are from the report that it generates. The first graph, is the latency of the API service, front-end service. So this subtracts any latency that's coming from the downstream service. We can see this is a histogram for that latency. We can see that it kind of overlaps, so there isn't much difference there. On the right side, we have number of calls per trace. So this kind of gives us the fan-out number for a single trace. So even this one looks pretty okay. But the middle one is overall latency for those kind of requests. And you can see a clear shift in that histogram. And basically, between the first batch and second batch, you can see that there is an increase in latency. This tool then goes a little bit deeper and gives you a breakdown of latency deltas between all the backend services that were contributing for this, let's say, endpoint or use case. And this bubbles up all the services that had higher delta. So with this, you can very quickly see that what services contributed towards this increase. Similarly, it gives you a breakdown for the downstream service calls or the fan-out. And there could be a change where instead of calling, one service is calling some downstream service too many times. And that might be a contribution towards adding this more latency. So again, this tool has been super useful. Without this tool, the performance team, they had to look at a lot of different dashboards and metrics and graphs to see where the latency increase is coming from. This tool just quickly gives them the answer. All right. So yeah, that's all that I want to cover on the automation side. We're doing a few more projects around automation, like anomaly detection, auto remediation, and error budgets, but maybe that's for another talk. Lessons learned. So one of the big lessons that I've learned over time is we should avoid tool fragmentation. So as the companies grow, different teams, they see that, hey, there's a gap in this tool, let me build my own tool. So for a single use case, for example, for metric system or for Logsearch, ideally there should be one tool in the company so that you can put in all your resources on that tool, make it the best possible tool, and then you are maintaining one tool. Unfortunately, sometimes things do get fragmented, then now you have to support multiple tools. And then the users, they also have bad experience because they have to learn 2 or 3 different tools, and they have to jump around between different tools to get the best use out of them. So yeah, and in long term, this can be very expensive because now you're maintaining all these tools and you're basically porting the features across different tools. Second thing is observability is challenging. It's not an easy problem to solve, especially as your company grows, as your usage grows, your volume grows. Just handling the scale could be really challenging. There are always new use cases that comes up. Educating users can be challenging because now you have to, let's say if you have 1,000 engineers, you have to make sure that they all understand how to use the tool in the best way. They're not abusing the tool. It's very easy to break these tools. So you can create one metric with such a high cardinality that your whole metrics pipeline can go down. So you have to then protect your tools against this kind of abuse. So yeah, observability comes with a lot of challenges. And observability is expensive. So when you're solving these challenges, of course, it's going to cost you money. It's expensive to store a lot of data. It's expensive to have engineers to build these tools, maintain these tools. In general, it's expensive because, and again, the reason is you're trying to solve a big problem. But it has a great ROI. So I think any dollar invested on observability gives you a good ROI because it helps all the engineers move faster. It adds more stability to your service. It basically helps you avoid big outages or recover quickly from different outages. It helps you move fast. So all the benefits that you get out of this, I would argue that the cost that you have to pay for these systems is totally justified. So here's our team. We are 6 engineers. We have 6 engineers and manager. It's a small team, really awesome engineers. I also want to acknowledge some other teams that we work closely with. Again, all these tools, it's not possible to build them reliably with a small set of teams. So for example, we have a storage and caching team. They manage our OpenTSDB HBase and the Goku, the new in-memory time series data. So we get support from them for our storage layer. Then there's logging team. They manage Kafka for us. We use Kafka for all our tools. So our metrics go through Kafka, our Logsearch goes through Kafka, our distributed trace data goes through Kafka. Then we have a big data platform team. They provide us support for compute platform where we run our Spark jobs to do different kind of processing. And we're hiring. So if you want to explore more about the opportunities at Pinterest, feel free to send us an email. And that's it. We're open for questions.
Thank you, Nauman. Okay, we have first question.
Three questions, but very short ones. You mentioned 800 million metrics, no logs in there, just metrics.
Yes.
Did you have to deal with providing the tooling for generating all those metrics from all the teams?
Yes. So we work with Service Framework team to provide libraries to instrument our code. And then we have a metrics agent that runs on the host. Our team basically maintains that metrics agent. And all services, they can just push their metrics to a local sidecar of metrics agent. And from there, we take over. We send them to Kafka. And from Kafka, it goes to our data store.
And have you had to deal with a lot of malformed events for metrics and logs? And how do you deal with them?
I'm sorry?
Malformed as in like events or metrics that are not formatted properly and would trash the system?
So if they're not formatted properly, we drop them. And we have a metric that shows that, hey, these many things are dropped. But if there are very high cardinality, then we have some mechanism to alert us, and then we blacklist those metrics.
Thank you. That was a great talk. You mentioned you do a sort of a chargeback system. That was very interesting. How did that go down with the teams that you approached that said, oh, hey, you said to them, you're generating, huge amounts of events and overwhelming us. Can you scale back a bit? Like, how did you deal with that difficult, well, it would be a difficult conversation to have with teams. How did you approach that?
So it can be difficult. Luckily, at our scale, we're still not a very big company. So we have good terms with those teams. They are also dependent on us for different things. So if we tell them that, hey, since they are our biggest users, they rely on us as well. So we can tell them that, hey, if you don't reduce the volume, you are going to suffer, that kind of thing. So far, we didn't have any issues. We're pretty friendly there. So yeah, it works out. But I can understand if the company is really big and there are so many teams, then it could become an issue.
Okay, in order to instrument the services as well, you probably use some libs, and they do the self-discovery of all the the path to how do you instrument the services, not only for the metrics?
How do we instrument services? So, like I said, we have service framework team that manages, they manage frameworks for different languages. So for Java, we were using Finnegal, and it comes with Ostrich metrics library. Similarly, for Python, we have built our own library. So we have libraries for different languages, and users can, we have documentation for that. They can use those libraries to instrument their services.
Thank you for the talk. I wanted to ask, you mentioned that you have to discourage your engineers from sending cardinality. What do you tend to get them to do instead?
What can they do instead? So certain cases, there are hard limits. So for metric system, after a certain number of cardinality, it just won't work. So that's where the reality hits in. So again, for that, for example, you cannot put a user ID as a tag in your metric. That will never work. There are workarounds, for example, tracing. In tracing, you can add more cardinality. Similarly, in logs, you can log more things. So for those kind of use cases, they usually use that. In certain cases, in the middle ground, what we do is we reduce cardinality for them. So again, a metric could be very high cardinality, and it's hard to read that metric. But in the background, we drop some tags so that for the other tags, they can still read those metrics.
Thank you, Nauman. And we run out of time, so let's give a big applause.
Thank you.